Yes, has to be changed. Good morning, and thank you for your presence today. I'm Francesco Puzzo. I'm the Research and Development Manager of Carrara SPA, Italy company which produce a sealing component. And I'm also the president of the association VALVEcampus that has in charge the organization of all conferences of the EVS event. And I finally also the chairman of the steering committee of this event 2024. Let me introduce very shortly, a very short presentation about a program, a research project program that we sponsored in order to improve our knowledge about the behavior of the polymeric seals under liquid hydrogen conditions. The driver of the project has been what happens at 4 degrees Kelvin under liquid hydrogen condition. The available literature on the behavior of plastic material in cryogenic application is extensive for nitrogen use, but quite limited for condition at hydrogen liquid condition. Because we have to take in consideration a development of the use of liquid hydrogen in the future, we decide to investigate about the behavior of some material. The first reference found about this theme in the web, I found one report dated December 97th from NASA and the Spacecraft Center Houston, seal material development program phase 1. The seal material development was planned in 3 different phases, and a total of 19 material were evaluated with the test carried on 14 material finally. This is the schema of the texture to test the valve. You can see in the bottom the jacket, and the valve that has been tested is inside to the jacket. The hydrogen flow inside to the jacket and go out through a vent in order to maintain constant the temperature to the liquid hydrogen. And from the right side, the helium gas flow in the valve when the valve is completely at the temperature of minus 269, I believe. The thermocouple were welded on the bottom of the valve in order to indicate the tested temperature. And the leakage was measured on the left side using a water displacement measurement apparatus for measure the leakage through the valve. Yes. This is the official procedure adopted to test the valve. Determine the valve seat load pressure on dome required to effect zero leakage with helium at ambient temperature, using helium to push through the jacket and the valve for 15 minutes, flowing liquid hydrogen up to when the thermocouple says that the temperature is okay. Calculate again the valve seat load pressure on dome to obtain zero leakage through valve. Please note that the term zero leakage are used in this case to denote no discernible helium leakage for a period of 5 minutes. using the apparatus that I said before, displacement measurement apparatus. Finally, cycle valve from 0 to 100 cycle. Again, determine seat load to effect zero leakage. Purge with helium and warm to approximately room ambient temperature. And finally, check again the seat load required to affect the sealing. So, thanks to the partnership between my association VALVEcampus, which is the sponsor of the project, DuPont Switzerland, Fluor Sears SPA, Fluor 10, and Victrex, we built up a project where the scope was the investigation of the mechanical behavior of different plastic at 4 Kelvin. Each supplier forwarded to the laboratory a set of samples in cylindric configuration, and the lab, aerospace and advanced composite laboratory in Austria performed the test, calculating the stress-strain behavior till the fracture of the sample. What we have tested? We have tested comprehensively 72 samples, belong to 3 chemical material, polyamide, PIC, and PCTFE. When you read the F1, 2, 3, etc., it means proprietary formulation. I mean that to produce this kind of material require a proprietary formulation, and each company select a method and the filler that is required to produce the item. So the polyamide A1 is different to the polyamide A2. This is the meaning. And also the PIC B1, C1, and C2 are different because are different formulation and the production method. We perform the test also to room temperature in order to calculate for benchmark the compression strength test and the compressive module of each item. And compressively, the number of tests at 4 Kelvin has been 24. Some detail about the test. The main trouble that the laboratory have to solve is to calculate the correction of the result in order to normalize the effect of the flexure of the sample during the test. This means that primarily the result follow the green line, and after correction the line move left because the result has been corrected. Okay. An overview of the machine adopted to test the material. This is a special machine able to make the compression test in an ambient where you can inlet the helium, liquid helium, in order to achieve the 4 Kelvin temperature. And this machine is able to perform this kind of test. Finally, this is the core of our research, is the aggregate result average of the data collected to 4 Kelvin. What is interesting in this table? We represent here the average of the result. It means that each line is the average of the result of 4 samples. I mean, the first line is polyamide. The result of the first formulation of the polyamide has been require a compressive strength of 465 megapascal, and the modulus calculated has been 6.64. And the 0.1% of field strength has been 314 megapascal. But in the right side of the table, you can find the most interesting result, because you can read the deformation of the material equivalent to the megapascal required to deform the material for 1%, 3%, 5%, and finally 10%. And you can read the different stress required to deform the item, and the difference of the compressive modulus between the different material. That's all. This is what we have finally, the final result of our investigation. Okay, the data collection, the project is not intended to classify finally the performance of the material. The scope of the investigation is not to say polyimide is better than PCTFE, etc., but only to get a look about the behavior of the material in this condition, because the data are really few in this field. And is planned to draft a technical paper, and we wanted to publish this document in an international magazine, and to diffuse this information to everybody, because the scope of the association is to share the result with the user. And now we are discussing with the partner a second round to test in next year the material in order to calculate the friction at liquid hydrogen condition. That is the second parameter that is important in order to evaluate the material for the seat of the valves. Finally, my sincere appreciation and thanks to the partner who participated in this project, DuPont Switzerland, in the person of Ruth Jakowiak, that is present, thank you, and Fluor Seals, Giovanni Dall'Olio, I don't see Giovanni, but Massimo Salogni of Fluor 10, and Christian Salvatori from Vitrex. Thank you, Christian. I'm not expert in this field. Please do not get a question about the material, because it's not my work. If you have some question, you can contact directly by mail this group of person. In few months, we will publish the result and become public. And finally, this presentation will be available on our website, VALVEcampus, because all presentation will be public. Also, my speaking will be on a YouTube channel, if you want to say again this history. Okay, thank you for your attention, and enjoy the show.